Hello. This is a video that's to introduce and explain how to use the Simulated Neural Moments package. The Simulated Neural Moments is a package for the Julia language. It's available as a registered Julia package, and it's also available from this GitHub archive you can see here. Okay. If you want to get the code and run the example, the easiest way, even if you have installed the Julia package, the easiest way to run the example is to go here to code and either git clone the package or download it as a zip someplace where you can easily get to on your hard drive. The reason is that when you install it in Julia, it's going to be somewhere hidden off in the Julia packages place, which is not easy to find. Okay. Now, what this package does is estimation and inference in a way that's very similar to the method of simulated moments or approximate Bayesian computing. The difference is that the statistics or moment conditions, which define the final estimator, are obtained by training a neural net to take raw statistics and recognize the parameter which generated the samples corresponding to the raw statistics. Okay, so the initial vector of moment conditions may be over-identifying, but when we pass it through the neural net, the final output of the neural net has the same dimension as the parameters of the model and is an exactly identifying statistic. And that is the statistic that is used for method of simulated moments. So we have exact identification, but using all of the information from the original statistics. Using all the information from the original statistics leads to good fit, and having an exactly identified estimator leads to accurate confidence intervals. And those claims are verified in these two papers, which are noted here. So now what I'd like to do is run through the example that accompanies the package. So if you downloaded the package in the way that I mentioned before to a place that you can find on your computer, you can go to the examples directory and look at this example file that we're looking at here. Okay. You need to activate the environment, which is the environment here in the project DOML file here. You activate the environment that accompanies the example, and we're ready to run. Okay, so the first thing we do in this first block using VS Code is we run that block to load in all of the needed packages. Okay, those are installed because we activated and instantiated the environment. Okay, that's done. The next thing we've got is a if block here, which allows the example to determine if it's being used as a test for the package or if it's an interactive run. We are doing an interactive run, so test mode is not defined, which means we're going to be in this first block here. These two lines, 13 and 14, you can select which of the two examples you want to run. The first is a stochastic volatility model with 3 parameters, and the second is a mixture of normals model with 5 parameters. So we're going to be running the stochastic volatility model. Line 15, you can select how many samples you would like to draw from the prior for training the net. If you leave that at 1, it's going to use a default, which is 20,000 samples for every parameter. So, for example, in the model we're looking at, we have 3 parameters, so it will draw 60,000 parameter draws from the prior. For each one of those parameter draws, it will draw a sample from the model, and with the sample, it will compute a vector of statistics. So in the end, we're going to have 60,000 parameters and 60,000 statistic vectors corresponding to each vector of parameters. Epochs here in line 16 is the number of epochs that we use to train the neural net. Okay, so we'll run this block to set that stuff up. Okay. The next thing we do in line 27 is draw a single quote-unquote real sample from the model. This is just an illustration, so we're going to draw it as generated data from the model, but if you had a real data set, you would load in your data from the real data set at this point here. Okay, run that. Whoops, run that. I have to click there first. Okay, there we go. So we have 500 observations from the stochastic volatility model. This next block here is setting up the S&M model structure, which defines the statistical model being estimated. Okay, so it gives the name of the data training process here, the sample size, lower bounds on parameters, and so forth, and some other items which are explained in the documentation. Okay, the other thing also you can notice that you can see the format these things have to have by looking at the svlib file, which is the model we're working with, and this gives you the format of all of the things that need to be defined in the S&M model structure. Okay, so okay, back to the example. Let's define that structure. Okay, and then the next block here is going to train the neural net. Okay, we pass it the structure of the model we're working with so that it knows how to generate data and so forth. The size of the number of draws we want to pick from the prior, which is the default here, which is going to be 60,000 for this in this case, and the number of epochs, which we defined previously. Okay, we run this block to do the training of the net. Okay, this will take a little while because it first has to generate 60,000 draws from the DGP, and then it needs to use Flux, which is a package for neural nets in Julia, to train the, in this case, it's a simple feed-forward net. Okay, so this gives us some information as we're working through the epochs. Over here to the right, you see the in green is the loss using the validation data, and if that stays green, it means we're improving at every new epoch. If that turns blue, it means that we did not improve. Okay, so we're still improving, and down here you see the relative RMSE. That is the RMSE in the validation set scaled by the standard deviation of the for each of the parameters from the prior. So we'd like to see this number less than 1, which means that the trained model is a better fit than just a draw from the prior, and this gives you an idea of which parameters are being fit better and which are less well fit. Okay, so you can see we're occasionally getting a blue out here. If we get 10 in a row, training will break out and stop. Otherwise, it will continue until we get to the maximum number of epochs, which was 1,000, is what we specified here in the code. Okay, we're still going along, about halfway done. Say hello again, just so you know that there's a human behind all this stuff. Okay, so the validation loss is still improving a little bit, not much. The relative RMSE is pretty much stabilized, so we're doing about as well as we can here, at least with this number of draws from the prior. By the way, I think I forgot to start Julia using threads, so this is a little slower than it would be normally. Okay, we're done training, and we can go on now to, in this block here, what we're doing is we're having a look at the transform statistics that were generated to train the net. What we wanted to look at is to make sure that we are not unduly affected by outliers. So I'm going to run this block, and that's going to give us box plots for each one of the statistics. And here, the main thing we want to see is that the box plots are not dominated entirely by the outliers. So if you can see some blue, it means that there are some outliers here, but we can see some blue, which means that between the whiskers, there's a fair amount of data that has not been unduly compressed, which means that the net is going to be able to fit reasonably well. It's going to be able to distinguish between the statistics because there is enough variation. Statistic 11 is the one that's most affected by outliers here, but we can still see some blue here, which means, and there's a distance between the whiskers, which means that we do have a fair amount of variation in the data that was used to train the net. Now, if you wanted to check what's going on with statistic 11, you'd go into your code and you'd examine what is statistic 11. Okay, where is that? Up here. Here are the auxiliary statistics. Well, we'd figure out which one of these is the 11th statistic, and we might want to try to robustify that a little bit to limit outliers. Okay, but we don't have an excessive problem here, so I'm not going to worry about that. Next block, you can save the results of the trained net if you'd like to, so you don't have to retrain it in case you'd like to make make use of this for multiple runs. Okay, I'm not going to bother with that. This block here is going to compute the raw output of the neural net, passing in the statistics that are generated by the real data here. Okay, and we execute that block, and that gives us this vector of parameter estimates here. Okay, those are the statistics which we're going to use for the method of simulated moments. Those are the real statistics, and then when we do simulation, we're going to be trying to find parameter values which lead to simulated statistics analogous to these, which are close to these. Okay, that's how we set up the method of simulated moments. Okay, here in this next block, we're setting up the controls for the Markov chain Monte Carlo. Okay, we're going to use S is important here. That's the number of simulations which are done to evaluate the likelihood function corresponding to the method of simulated moments. This is the limited information likelihood following Kwan 1999 or Kim 2002, and that we're going to compute the limited information likelihood, which is used to do the Markov chain Monte Carlo using the methods of Chernozhukov and Hong 2003. Okay, so this is the number of simulations. This is the number of draws in line 60 is the number of draws used to compute the covariance of the proposal density. And in 61, we have the length of the Markov chain. 62 is the number of burn-in draws in the Markov chain that we're going to drop to avoid startup effects. Okay, I'll run this here. We've got a tuning parameter which will affect the proposal. Okay, down here, this line 72 is computing the proposal covariance, which is done by taking the estimate we got from the neural net, and we're going to make covreps draws from the data generating process at that parameter value. And for each one of those draws, we're going to compute the neural net statistic. So we'll end up having a number of replications of that statistic, and the covariance, the sample covariance of those replications will define the covariance of the proposal distribution, scaled by a tuning parameter, which is by default 1 here. Okay, and then line 74 is computing the limited information likelihood function using the continuously updated version of GMM following Quan 1999 or Kim 2002, with the variation that we're using continuous updated GMM rather than two-step. Okay, execute that block to define those things. Down here, we're going to run a short MCMC chain to allow us to improve the proposal density. Okay, so we'll do 1,000 draws. Okay, we're seeing the result there. The acceptance rate is a little on the high side, a little bit above around 43%, which is a little higher than we would like. This block here is used to refine the proposal. Okay, so instead of using that initial covariance for the proposal, now we're going to take the covariance of this short chain, and we're going to then also alter the tuning parameter, reducing it if we had too low of an acceptance rate and increasing it if it's too high. So in our case, we'll be increasing the tuning a little bit and define this second proposal density. Okay, and once we have that, we'll do another Markov chain using the full length this time of 5,000 with this new proposal. Okay, I'll run that. Now this is just an example the way I've defined this proposal 2. It's the user's responsibility to define the proposal in a way that leads to effective sampling with an appropriate acceptance rate. You can see the acceptance rate is a little high still, but it's better than it was. If I wanted to, I could embed this block here inside of a loop until the acceptance rate got to the target I was after, but I'm not going to do that with this simple example. One comment also is that the proposal density here is very closely related to the limited information likelihood function, so if we ignore the effect of the prior, this proposal is close to the posterior because the likelihood function converges to the posterior as our sample size gets large. So that's the reason why this proposal can be effective and why ordinary Metropolis Hastings acceptance rejection can work well in this application. It's because we have a good idea of what the asymptotic likelihood looks like, and we make the proposal look very similar to the likelihood function. Okay, that's all done. We got the end is, and then finally in the next block we can look at the results. Okay, one thing you get is a plot of the chain. Okay, we got some chains which look pretty good for the 3 parameters, and you, in the right hand side, you see the posterior for the parameters. Okay, they look reasonably smooth. You also get a plot of the likelihood value corresponding to each trial draw of the parameters. Okay, and down here we have the results of the okay, we convert the output of the chain into a MCMC chains object, so we can look at that. We adjust the window size here. That doesn't want to work. Okay, so we have 5,000 draws. The means of the parameters are here. The effective sample size. Oops, where'd it go? Here is Okay, the effective sample size is okay. Here are the medians of the parameters, and for reference, here are the true parameter values. So you can see that, why can I not make that plot go away? Okay, there we go. Trying to make this bigger. Okay, where are we? Here's the true parameters down here in green, and you can see that the median parameters, 0.63, 0.69 is the true value. The medians are pretty close to the true parameter values. Okay, so things work pretty well in this run, and also the means up here are pretty close to the true parameter values. Okay, so that's an example of how to use this. If we go back to the example code, you can up here you can run the other example, which is the multivariate normal model. If you like, you can just uncomment that and then rerun this, and you'll see another example with 5 parameters instead of just 3. Okay, I'll stop that here.